This video covers section 3 of chapter 4. In this section, we will talk more about summarizing quantitative variables and begin work on the normal distribution. We'll talk about the relationship between the mean and the median. We'll introduce the standard deviation as a measure of spread, and we'll talk about normally shaped distributions. This section falls under displaying and summarizing data for one quantitative variable. In the last section, we mentioned two ways to measure center and spread. The first was the 5-number summary, which we looked at last time. The second is the mean and the standard deviation. Let's start by focusing on the mean. The mean is the arithmetic average of your set of values. The word arithmetic here has a very particular mathematical meaning, and it tells you how we compute this mean. If we have n values in our sample, we call the mean x bar and denote it with an x with a little line over the top. To compute it, you add up all n of your data values, take that sum and divide it by n. This is the average that you're accustomed to seeing. If we're looking at a population instead of a sample, we'll use the Greek letter mu to denote the mean. So when you see x bar, that is a statistic because it applies to a sample. When you see mu, you're talking about a parameter because it applies to a population. Here's an example of computing a mean. From our student survey data, the 14 other students have taken the following numbers of credits. What is the mean of this data set? Well, this is a sample. We'll call it x bar. We add all those numbers up, divide the result by 14, and we get a mean of 13. Let's look at an example comparing the mean and the median. With this same data set, we can see that the median is 13.5. We actually saw this in the last video, and we just computed the mean to be 13. In this case, why is the mean less than the median? Whenever you have a skewed data set, that means, remember, that you have several unusually low or unusually high values. Unusually high values don't affect the median, nor do unusually low values, but they do affect the mean. In this case, since this distribution has a left-handed tail, it's skewed to the left, these low data values will pull the mean away from the median in that direction. Here's another example. If we look at the output for students' computer times, again from the student survey data, using a computer we can find for these 20 data points a mean of 97.9 and a median of 60. Here the mean is quite a bit higher than the median. Why? Again, if you look at this distribution, we see one peak and a very pronounced tail to the right. This data set is skewed right. Those unusually high values for this variable pull the mean in the direction of the tail. To summarize, if the distribution is symmetric, the mean and the median will be about the same. If the distribution is skewed left, because there are low outliers, the mean will be pulled to the left, so it will be smaller than the median. And if the distribution is skewed to the right, the mean will be pulled in that direction, so the mean would be greater than the median. So, if you're asked to summarize a single quantitative variable, which should you use to report the center, the mean, or the median? In general, if there is skewness, a pronounced skewness, to either the left or the right, a better way to summarize the center is the median. However, if there is no pronounced skewness, report the mean. Now that we've covered the mean, let's talk about the standard deviation. The standard deviation is, at its heart, something like the average of how far each data point is from the mean. To compute it, you subtract the mean from every value in your data set, square each of those results, add them up, divide by n minus 1, and then take the square root of that result. Luckily, you do not need to have that formula memorized. Your computer and your calculator will do it for you. But it's worth knowing where this comes from. If this were truly an average, you probably would expect this denominator to look not like n minus 1, but like an n. In general, dividing by n minus 1 instead of n does a better job when we're working with a sample. The reason for this is very technical, and we won't get into it. Let's look at an example using our calculator to find the standard deviation. First, excuse my cat. We need to enter the data by clicking on the Stat button. We want to edit our data, so we'll select option 1. Then we want to enter the data we wish to analyze into L1. Yeah. So let's just pick a few numbers. 12, 25, 22, 23, 15, and 20. Now I'll go back to the Stat menu, and now I want to do a calculation. So I will push the arrow button to go over to Calc, and I want to calculate one variable statistics. So I'll press Enter. My data are in L1, so that's the right thing. Frequency list we don't need to worry about. Let's leave it blank. So let's go down and calculate. What this shows us is a lot of pieces of information that we're going to be interested in. First, here we have X bar, that's the mean. The mean of our data set is 19.5. Next is the sum of all our data points, 117. The sum of the squares of our data points is something that we're not going to need. The standard deviation is given in the next two entries, Sx and sigma x. The one we want to choose depends on whether our data comes from a sample or from a population. Sx is the sample standard deviation. If our data comes from a sample, the standard deviation is a little bit bigger than 5. If our data set represents an entire population, the standard deviation is 4.57. N gives us the number of data points, 6. And then as we scroll down, min x, q1, median, q3, and max x are the 5-number summary. How do we interpret these numbers? The mean is the typical value. It's a measure of the center of the data set. So the mean is sort of our average value. The standard deviation is a measure of spread. It tells you how far away from the mean the typical data point is. It's this interpretation that we're really concerned about. The actual calculation is something we're not ever going to do by hand, so I'm more worried about you being able to interpret the standard deviation rather than compute it directly. Let's look at an example. The household size in the United States has mean approximately 2.5 people. Which of these is a reasonable option for the standard deviation? Well, the answer is 1.4. The reason why is we expect the household size to be about 2.5, give or take how much? But the first option, 0.014, if you go up and down from 2.5 by that much, you're still very close to 2.5. There are plenty of households that have more than 3 or fewer than 2 people living in them. We have the same problem with 0.14. It's too small. 14 is way too big. That would tell us that it wouldn't be unusual to have a household of size 2.5 plus 14, which would be 16.5 people. But it also means it wouldn't be unusual to have a household with size 2.5 minus 14, which is very, very negative. 1.4 is the only reasonable response. So if the mean is 2.5 and the standard deviation is 1.4, about how many standard deviations above the mean is a household with 4 people? 4 is 1.5 more than 2.5, and 1.5 is a little bit bigger than 1.4. So 4 is a little bit more than 1 standard deviation above the mean. This is a computation that we'll do frequently, especially when we're doing inference. Let's consider another example. Consider the ages of students and guess the standard deviation of all students in a high school where the mean is about 16, the standard deviation of the ages of all high school seniors with a mean around 18, and the ages of all students at a university where the mean is about 20.5. If you think about students in a high school, typically a student would be within 1 year of 16 years old. Certainly not every student is within 1 year of 16 years old, but it's probably safe to say most students are within 1 year of 16 years old. If you narrow it down to high school seniors, most of them are close to the same age, about 18, so we would expect that standard deviation to be smaller, on the order of a few months. The ages of all students at a university, while the mean is about 20.5, there will tend to be a little bit more spread in students at a university once you include students who are non-traditional, who are coming back for their education after they've been away for a while. So that standard deviation I would expect to be a little bit bigger, 2 or 3 years. Of course, we don't have data for this, but being able to pick a standard deviation or look at a standard deviation and see if it seems reasonable is an important thing to be able to do. Always ask yourself when you're doing these computations if the result you get seems reasonable. Let's take a look at an example. Here's a list of some heights in inches. What's the standard deviation? Well, remember, the standard deviation is the square root of the average squared deviation from the mean. First, we compute the mean, which happens to be 67. Then we compute the deviations from mean, which is what we get when we subtract from the mean. So 64 minus 67 is -3. When we do that for all these numbers, we get -3, -1, 0, 0, 1, and 3. Next, we square the deviations, which gets rid of the minus signs. Then we compute the average. Average here is in quotation marks since this is a sample. The computation for the sample standard deviation requires us to subtract by the number of data points we have minus 1. So this is not truly an average. We'd use the actual average if this was a population, but since this is a sample, we'll subtract 1 from that denominator. That gives us a 4. Finally, to get the standard deviation, we take the square root of this number. The standard deviation is 2. That's the typical distance from the average height. And sure enough, if you add 2 and subtract 2 from the mean, you get a range of 65 to 69, which includes most of the data points. Here's another example. If we compute the statistics for the sample from the student survey data on student earnings, here are the numbers we get. Notice that these numbers are reported in thousands. The average is 3.776, which corresponds to $3,776. The standard deviation is then $6,503. So looking at the histogram, does it make sense to say that students averaged $3,776, give or take about $6,500? That's not a really good depiction of what's going on here. This distribution is very strongly right skewed. Remember, that means that it pulls the mean away from the median. The standard deviation also gets skewed. Notice how the standard deviation is far, far bigger than the actual mean. If you go up and down by $6,500, you'll end up with some very negative numbers, which don't really make sense in this context. Actually, most of the data fall within $2,000 of $2,000. When your data are very skewed, like this, the 5-number summary is a much better way to summarize the data. If your histogram, though, follows the normal curve, using the standard deviation is a great thing to do. Remember that a symmetric distribution means that it's just as likely for a value to be a certain distance above as below the mean. In other words, the shape of the distribution looks the same on one side as it does the other. That's why we use the word symmetric. If the shape of the distribution is normal, the mean and the median are the same. A distribution is bell-shaped if the highest values are closest to the mean, and as we move away from the mean, the frequency goes down. That gives us tails on both sides. When we look at a histogram, we will always scale it so that what we're looking at when we measure areas, we get percentages of responses. That means the total area under any histogram is always 1, or 100%. Here's a histogram of a typical data set that approximately follows a normal distribution. This is a histogram, so the total area of all these boxes is 100%. Notice that the peak corresponds with the mean, and that's also approximately where the median is. If you look on either side of the mean, it's almost like the mean represents a mirror. The shape is about the same on both sides. There's a peak in the middle and tails on both sides. We know that IQs are normally distributed with a mean of 100. Here's what a typical histogram would look like. What percentage of people in our sample would we expect to be between 90 and 120? The percentage of respondents that would fall between 90 and 120 in IQ corresponds to the area that's shaded in the darker blue. Eyeballing it, it looks like it's about 2/3 of the area, which would correspond to 67%. We'll find the precise number later. Many sets of data approximately follow the normal distribution. If we know the shape is normal, and we know the mean and the standard deviation, then we can compute the percentage of values over any interval we want. For basic estimations, we'll use this rule. The empirical rule, or the 68, 95, 99.7 rule, says that when we have a normal data set, 68% of the points will be within one standard deviation of the mean, 95% will be within two standard deviations of the mean, and 99.7, nearly all, will be within three standard deviations of the mean. Put another way, if we represent the mean using x bar and the standard deviation using s, then a normally distributed data set will have these properties. 68% of the data will fall in the range between the mean minus one standard deviation and the mean plus one standard deviation. 95% of the data will fall between the mean minus two standard deviations and the mean plus two standard deviations. And 99.7% of the data will fall between the mean minus three standard deviations and the mean plus three standard deviations. So if we want to sketch a histogram, if we say that shoe sizes for 163 adult males is normally distributed with mean of 11 and standard deviation 1.5, we know that the shape of the histogram would look bell-shaped, like the one depicted here. We know the mean would go right in the middle, and you see the 11 here. And the standard deviation is 1.5. So we'll count up by 1.5s to 12.5, 14, and 15.5, and count down by 1.5. That gives us a good depiction of the range of the histogram. So to summarize, with the same situation, we're looking at shoe sizes normally distributed with mean of 11, standard deviation 1.5. The 68, 95, 99.5 rule tells us that 68% of the data will be within one standard deviation of the mean. So if we subtract 1.5 and add 1.5 from 11, we get the range 9.5 to 12.5. 95% will be within two standard deviations. 2 times 1.5 is 3, so if we add and subtract 3 from 11, we get 8 and 14. So 95% would have shoe size between 8 and 14. And 99.7% would be in the range from 6.5 to 15.5. That's 11 plus or minus 3 times 1.5, or 11 plus or minus 4.5. We can also use this rule to estimate percentages in the tails. Again, with the same data set, what if we want to know what percentage fall less than 9.5? We know that 68% fall between 9.5 and 12.5. That's in this range. But we're interested in what comes to the left, less than 9.5. Well, if 68% is in between those, that leaves 32% elsewhere. Since the tails are symmetric, that means the tails have the same size, half of that 32, which is 16%, will fall to the left of 9.5. We could also say that 16% falls to the right of 12.5. A related but slightly different question is, what size marks the top end of the bottom 2.5%? In other words, where would we cut off the left-hand tail so that the area in the tail is 2.5%? Well, we know that 95% of the data fall between size 8 and size 14. That's within two standard deviations of the mean. So half of that, or 2.5%, would be below 8. There's our tail. The histograms we've seen so far look like bar graphs, and they are. But if our quantitative variable has infinitely many possible values over a continuous range, so shoe sizes are not continuous because there's no such thing as shoe size 11.23794. Maybe we're measuring foot lengths. And we have infinitely many individuals in our sample. So maybe we're looking at infinitely many college males, not just a sample. And imagine that the values are measured to accuracy as precise as could possibly be measured. So decimals as long as you can think of. In that case, the histogram looks like a smooth curve. And if the shape is normal, the result is called the normal curve. So imagine our bar chart where all those steps get smoothed out. This is what the normal curve looks like. In this lecture, we talked about summarizing quantitative variables. We talked about the mean and interpreted it as a typical value of our data set. We talked about how the mean is affected by the shape of the graph, and how if there's a long tail to the right, for example, the mean will get pulled to the right, away from the median. The standard deviation is a measure of the typical distance that values fall away from the mean. Remember that the mean and the standard deviation are both affected by outliers and by skewness of the distribution. The normal distribution is a symmetric bell-shaped distribution. When we have a normal distribution, we can use the 98, 95, 99.7 rule to find key values or key areas underneath the curve. And we talked about sketching a normal histogram and the normal curve.